The rest can be taken care by electron correlation, which is going to be the next topic. I wanted to do something about it, but maybe next class. The rest is actually electron correlation. Why is it important? It's important because the entire chemistry is about difference of two large energies. For example, you are doing a hydrogen bond. We know hydrogen bond is a few kilojoules per mole. Of two large systems whose energies may be thousands of kilojoules, millions of kilojoules. If you calculate by Hartree Fock, you are making an error in both. The percentage of error may be very small, but that percentage error would be more than the difference. So if you are subtracting 1 million minus 1 million 1 by Hartree Fock, it's a terrible thing because 1 million is not 1 million. 1 million plus minus 1% or 2%. 1 million 1 is also plus minus 2%. So it's a nonsense result, right? You do spectroscopy. It's the same problem. You have excited state minus ground state. If you want to do, organic chemists want to do geometry optimization, it's the same problem because when you say geometry optimization, energy at one configuration versus energy at another configuration. So if you look at entire chemistry, it's all about relative energies. Difference of energies and two large energies, whose difference is less than the 1%, very often less than the 1% of the total energy. And that puts a lot of problem to the chemists, because that is what is called spectroscopic accuracy. That get me a number, difference of numbers, which is kilojoules, 2 kilojoules, 3 kilojoules, correctly. If you look at binding energy of a molecule, it's the same problem. Two large molecules, binding energy is very small. So the whole of chemistry is about difference, small difference arising from two large values. So even though Hartree Fock recovers 97, 98% of the total energy, it's not good enough. And this is where this very important topic of electron correlation comes in. How do I go beyond Hartree Fock? Sorry. How do I go beyond Hartree Fock? So that is where this entire issue will come up. How do I improve my single determinant? Although it's a very simple picture, because single determinant also tells me a very simple thing, that there are n electrons, n spin orbitals. So very simple, these diagrams I can draw. Just like I told you spin adapted state, I have to do combination of two determinants. So you have the alpha, beta, beta orbital mixing. If there is a mixing of spatial orbitals, it is even more complicated. And we don't know where the electrons are. It's the average of various things, just like in superposition, of wave function in quantum mechanics. So it's the same problem. So, but that is something that we have to do. Now, when you do this, a very important problem that is realized is what is called Coulomb hole. I'll just physically explain the problem. If you look at Hamiltonian, and this is understood, that if two electrons come very close to each other, of course electrons or particles cannot be traced, but when I say close to each other, it means in the Hamiltonian, if an Rij becomes close to 0, then the Hamiltonian can be loosely called a singular Hamiltonian. And the only solution that is allowed for a finite energy is 0 for such a Hamiltonian. So in general, we can say that at limit Ri tending to Rj, a psi will go to 0. So what does it mean? It means that there is a vanishing probability, in a very classical sense, there is a vanishing probability of electrons coming close together. Okay, again, it's a very classical interpretation, of course, which means the two coordinates cannot be together. This is a very strong part of the correlation. We have to see that all our wave functions must satisfy this. Does the single determinant satisfy this? That is something we'll ask. This is actually in a very loose manner called Coulomb hole. It comes from the Coulomb hole because the wave function goes to 0. So there is no probability of the electrons being there. So we will later see, particularly when you do density functional theory, there is a lot of interesting discussion here, how to satisfy the Coulomb hole. If you look at our single determinant, and let's say I simplify this to a closed shell ground state. So let us say that my RT form that I get is phi 1 alpha, phi 1 beta. So I get my phi 1. It's a 1s square function. Now, in a very loose sense, the two electrons, they can be alpha and beta, but they are in the same space orbital. Right? What can happen now? Because they are in the same space orbital, it is likely that the electrons, it's again a very physical picture. It is very likely that the electrons can be close to each other because I have an antiparallel spin. So both of them are lying in phi 1. Of course, if it is parallel spin, for example, if this would be also alpha, then this had to be phi 2. And then they would actually span the different space path. So it is quite likely they will avoid each other. So in a single determinant, this avoiding is automatic for parallel spins. So parallel spins, again in a very physical manner, they can avoid each other. Because they are usually, they have to be in different space paths. So there is a less likelihood of their probability. So later on we will do actually density metrics and we will show this to the density metrics that, what happens to the density. But this I am just making a very physical picture now. So parallel spins actually avoid each other. So that is already built in. What is not built in here is the antiparallel spins. However, if you look at the actual wave function, be it parallel, be it antiparallel, they must avoid each other. And that is the stronger hole called the Coulomb hole. What is satisfied for a single determinant is the parallel spin hole. And this is called the Fermi hole. It's very clear, the name is very clear, because the Fermi hole is satisfied because of Fermi exclusion, Fermi principle, Fermi statistics, and Pauli principle. So that is automatically satisfied. But the Coulomb hole is not satisfied. So when you go beyond single determinant, physically, and this is something that I'm introducing, but DFT has actually tried to address this, that the Fermi hole, while it is satisfied, we have to actually satisfy a bigger hole. That's the Coulomb hole, much general, more general hole. So in a way, electron correlation is said to be an exercise in correlating antiparallel spins. Because parallel spin correlation to some extent is already included. Please note that any correlation means avoiding each other. They can't come close. So for parallel spin, this is somewhat included in the single determinant picture because they have to have different space path. But for antiparallel spin, there is a less chance of avoiding. So when the electron correlation started in the 1940s, people were looking at a very physical picture. They said this is something that we have to build in. At least one important physical picture of correlating antiparallel spins. And this is where later these two concepts came, Fermi hole and Coulomb hole. And we have to, when you go to the DFT later, I think there are classes in DFT next week, we will actually look at how does the density functional theory or density matrix theory first and then density functional theory satisfy Coulomb and Fermi. What exactly does it mean in terms of density? And a lot of DFT people, when they develop exchange correlation potentials, they discuss whether these potentials is satisfying both the holes accurately, appropriately. But at this point, I just wanted to define these two terms. We'll come back in the context of DFT in a more rigorous way. So what we'll do tomorrow, I think tomorrow there is a change in the...
Yeah.
So you already announced. Yeah. So when is my class? 2 o'clock? 2 o'clock. So tomorrow my class is at 2 o'clock. I'm actually going to look at very broadly the overview of methods to include electron correlation. Now this is actually a big saga, so I cannot cover in one hour. I'm going to look at configuration interaction, which is basically what we call diagonalization over determinants. In physicists call it diagonalization. Exact diagonalization is in our term full configuration interaction, full CI. I'm going to also look at perturbation theory as one example. And then, of course, there are cluster expansion methods, which are basically known in chemistry as coupled cluster methods. Quite clearly, I can't cover anything in one hour. So that's why I've given a title overview of wave function methods. And the reason I'm going a little bit more deeply into DFT, because I think there will be more discussion on DFT, I guess, at at least for the solid state context. So that is the reason I wanted to cover more of this. And less of wave function method, but I have promised to some, if those who are interested, I will look at couple cluster in greater detail. That will require at least 10-15 lectures, proper lectures.
So you will not talk about variation in Monte Carlo?
No.
Wave function?
Yeah, but I mean, there are so many. Yeah. It's impossible in 1 hour. So I have called it an overview of a function method. So just to tell you how do you approach the problem? Rather than like perturbation method is an approach. What do you do? How do you build the perturbation theory? How do you build the configuration interaction as a linear combination? What do you do in cluster expansion method? And not into the details of solution of the equations and so on. Okay? But I think that is very important, and many will require, of course, the knowledge of several other techniques, particularly second quantization, which many of you have. But more importantly, diagrammatics. I think again, most of the physics students probably have diagrams, right? Feynman diagrams at least. So many of those techniques make it very simple, but they have to be introduced in a proper manner. So I will just give a broad rundown of what are the methods available to us to calculate electron correlation. And first, what is electron correlation? Of course, I'm beginning. So the electron correlation is anything that you can do to improve Hartree-Fock. So Hartree-Fock wave function is the best uncorrelated wave function. So the best uncorrelated wave function is called Hartree-Fock. Anything beyond Hartree-Fock improvement is actually part of electron correlation. So in a sense, Hartree-Fock is the zero line. So after this correlation will start, and the difference of the total energy and the Hartree-Fock energy is what is known as the correlation energy. So you calculate Hartree-Fock energy by this average value. Psi, this will become my Hartree-Fock energy once I solve the equation. And then my E naught minus E Hartree-Fock is what I will call correlation energy. We know that the Hartree-Fock is above E naught, so how do I get to these numbers? Can I always have variation principle? Can my better method go like this? So there are a lot of issues which will come up. And how do I improve this? You have to remember that almost from 1950s till today, so which is in almost 70 years, that there have been exercises in this. How to improve methods, because we don't have exact methods. I think that's the first thing to tell, that for many particle problems, we don't have exact methods. So no method can be exact, it's only approximate methods. So how do I develop this approximate? For a physics problem, many times the band structure is good enough, as we are discussing, because you don't need to improve further. But in chemistry, as I told, we need to go beyond Hartree-Fock. And that is why I think there's a great departure of chemistry and physics in terms of emphasis. However, the techniques that we'll use are all from physics. Correlation, variation, similarity transformation, mathematics and physics, insights. So that is why I think it has been interesting that the physicists, many physicists of course have played a very important role in development of the subject. But many haven't taken that much interest, because it's not the main focus of the physics to include the small improvement of the numbers. So in that sense, DFT has been very attractive to physicists, because DFT gives a broad idea, whereas DFT has been questioned, ironically, much more by chemists. Although Walter Kohn got Nobel Prize in chemistry, and I always say this, that Kohn should have actually got in physics. But Kohn got Nobel Prize in chemistry, and chemists have used, abused, used DFT also most, have criticized DFT also most. And today, of course, DFT is an acronym that all students know. This 3 letter is very, very important, DFT. So, I mean, I am amazed actually when experimentalists give result that I did a dye-sensitized solar cell, this is my efficiency, experimental number. Then they said, I don't have faith in experiment, I have vetted this by DFT calculation. And actually, I said, you are vetting the experiment by DFT calculation. So many years fight for the time being. So, there is a big fight between the wave function people and DFT in the chemistry community. Yes? So it's stop here.